Yeah, it's 9:30 a.m. here. Morning.
Okay, yeah. So this Monday evening here.
Oh, it's Tuesday morning here.
Yeah.
So how is working environment at Calgary? I mean, what are the courses, undergraduate, postgraduate, or in civil engineering core branches are there?
Yeah, so I'm working in the transportation group. So we have a big transportation group in the University of Calgary. So, but we have also other departments in the engineering faculty, including civil engineering. We have chemical engineering, electrical engineering, computer engineering, I think all types of engineering fields.
Okay. So transportation would be a separate group or department?
So transportation is under civil engineering department, but it's also a minor.
Okay.
So students can specialize. They can have a degree in civil engineering and they can minor in transportation engineering.
Got it. It would be undergraduate only. Degree would be undergraduate.
Yeah, but we have a master's and a PhD program also in transportation engineering.
Okay. In our university also, we have an undergraduate program in civil engineering, postgraduate program in transportation, geotechnical and structural engineering, and we run PhD program also.
Oh, that's great.
We'll invite you further for evaluation of thesis and maybe more expert lectures, sir.
Yeah, that would be great, and I will do the same. Yeah, from our side.
Yeah, thank you.
Yeah. So how many participants are we expecting for today's session?
Yesterday we had 77 participants. It's varying based upon their interest. So we expect at least 60-70 participants. So, and yet it is only 2 minutes after 9:30. So we wait for few minutes more, right? And
Yeah.
we'll start at 9:35 a.m. sharp. It is 9:32. So we wait for 3 minutes and then definitely we'll start the session.
Yeah, that's great.
Sorry for that inconvenience and waiting period.
No, we are still on time. Yeah.
And how long is the postgraduate program over there? 1 year or 2 year?
So master's degree is usually a 2-year program. A PhD is usually 4 to 5 years. It depends on the project and the students. But a master's degree, for example, students are allowed to finish the master's degree within 4 years period. But most of the students will finish it by average within 2 years. And some students, they will take 1.5 years.
Okay, it's flexible.
Yeah, so students will be given up to a maximum of 4 years to finish the master's degree. And the PhD usually by average student would take 4 to 5 years.
Okay. And do you have a dissertation or research project kind of thing in program?
So for the master's program, we have thesis-based master's program and project-based or course-based. So we don't call it thesis.
Okay.
So we admit students if they want a thesis-based master's degree or a course-based master's degree. But for the PhD, obviously, everyone will do a thesis.
Okay. So thesis-based programs you run.
So most students choose the thesis-based master's program because there is also a grant associated to it. So whenever we admit students in the master's program, most of the time we should guarantee they will be funded for 2 years. And most students choose a thesis-based master's program, but we also have a course-based master's program. And students, when they finish their master's program, they don't have to do a thesis project.
Okay. Okay, let me send one note to all participants group, and then we'll start, sir.
All right.
Okay, so very warm good morning to all the participants. Welcome to the second day of the STTP on Artificial Intelligence, Internet of Things, and Nanotechnology application in civil engineering. Yesterday, we completed 3 sessions and we learned that from the different speaker, what is the AI fundamental, what is the IoT fundamental, and last speaker taught us about the fuzzy logic application in concrete mix design. Today with us, a very eminent speaker with us, Dr. Merkebe Demissie, who is assistant professor at Department of Civil Engineering at University of Calgary, Canada. We express our deep gratitude to you, sir, because you accepted our invitation, and though there is a huge time lapse and you are here with us, stretching yourself and sparing your valuable time and energy. So to introduce him, he was a research associate and postdoctoral fellow at the University of Calgary. And before joining University of Calgary, he was a postdoctoral fellow at University of Coimbra, Portugal. And we got the reference of Dr. Merkebe with our beloved professor, Dr. Dinesh Kumar. He was also, I think, postdoctoral fellow at University of Coimbra, Portugal, right? Okay. And Dr. Demissie received his PhD in transport system from MIT Portugal program, a joint program between Massachusetts Institute of Technology and selected Portuguese universities. The MSc degree in transport system from Royal Institute of Technology, Sweden, and the BSc degree in textile and manufacturing engineering from the Bahar Dar University of Ethiopia. So this is the time to now hand over the session to Dr. Merkebe. So over to you, sir. Aditya sir, may I request you to share the sharing rights with Dr. Merkebe?
Okay, sir.
Can you see my screen?
Yes, yes.
All right, so thank you for the generous introduction. And Thank you also for inviting me to present for this research seminar. So today I'm going to speak about a research topic from my research program, leveraging big data analytics to improve transportation planning and operation. This is the outline of my research seminar. So I will start talking about emerging transportation technologies and services. Then I'll talk about my research vision and research contributions in 3 different topics that are relevant application of big data analytics in transportation systems. Then I'll talk about a future research plan associated to my research program. So I'll start my my discussion with emerging transportation technologies and services. So as you know, in recent times, we have a different emerging mobility services and emerging transportation technologies. These are related to electric vehicle, connected vehicle, and also vehicle automation. And also we have a number of on-demand mobility services. All these emerging transportation technologies generate big data that can be used to characterize the movement of vehicles and freight and other activities. So these emerging mobility services and technologies, they have some benefits, for example, in terms of improving safety, reducing emission, and also improving accessibility. We also have other type of benefits in terms of reducing costs for the government and for the users. And one of the important benefits of these emerging mobility services and technologies is reduction of auto ownership. We also have diverse big data generated from these emerging technologies. Of course, we also have some disadvantage associated to these emerging mobility services and technologies because of these on-demand emerging mobility services. We have seen an increased number of trips. Because of this, an increased number of trips, we have seen vehicle kilometer traveled increase. That's associated to increased congestion, increased emission, and so on. Because of this big data generation, we also see some issue with privacy. The other major problem is the equity performance of these emerging mobility services. So most of these services may not provide benefits for diverse population groups. For example, if we can see Uber or shared electric scooter services and so on, they are not disabled friendly, or they will not be accessible by people who doesn't have a smartphone and so on. So there might be some questions related to some issues related to the equity performance of these emerging mobility services. So due to these emerging mobility services and transportation technologies, what actually changed is the way we access activity locations. Otherwise, the drive to do activity didn't change. The only thing that changed is most of our trips are now multimodal. Previously, we might be using one type of transportation modes to access different activity locations, the likes of access to our workplace or going to shopping or other activity location. But now, because of these diverse mobility options, our trip making behavior might be more multimodal. So because of the paradigm shift in terms of from traditional transportation modes into a more flexible on-demand emerging mobility services, some of the trip characteristics are changing, and also our traditional models, for example, the classical 4-step traditional models may not be flexible to accommodate some of these emerging mobility services and integrated services, the likes of mobility as a service. So we might need a new set of data to capture the behavioral dynamics, interaction, and evolution of both the transport supply and demand side. Unfortunately, this availability of traditional datasets for mobility analysis will remain as one of the transportation planning and operation concerns. The advantage, on the other hand, the positive side is we have a lot of emerging big data sources that can be used to build models. And also we can also take advantage of state-of-the-art big data analytic concepts and data-driven transportation models to address some of these challenges and research gaps. So in my research group at the University of Calgary, my research vision is to apply big data analytics, data-driven models, and other transportation planning concepts to study how to increase operational efficiency, improve passenger experience, and facilitate development of new business models for emerging transportation services, public transit, and the freight and logistics sectors. So when we talk about big data sources, we have different types of big data sources relevant to transportation systems. I put these big data sources into 4 different categories. The first category is purposely sensed data. These are basically traditional agency data from the transportation systems point of view. Most of these traditional agency data are related to surveys and also some of the devices we installed in, for example, public transit, passenger counting system, automated vehicle location system, and so on. The data we get from those sources. The second category is opportunistic sensing data. This type of big data sources are data sets that can be generated from other sources, but we can use them as a proxy to characterize the movement of vehicles, freight, and other activities. We also have data sources, crowd sensing data, the likes of Foursquare and social media data. We also have another category more closely related to crowd sensing data, volunteered geographic information data sets. One particular example is OpenStreetMap. Then today, I'm going to discuss 3 main research contributions from my research group. The first research contribution is understanding travel using mobile phone data. This is for passenger transportation system. The second one is freight truck travel demand modeling using GPS data. This one is the second one. The second topic is using emerging big data sets to model freight, the movement of freight and commercial vehicles, the likes of GPS data and other business establishment data sets. The third category is using big data sources to model micromobility, specifically shared electric scooter services. Then I'll start the first topic, understanding travel using mobile phone data. So we have this mobile phone data generated by telecom companies. This is a typical example of opportunistic data set for transportation planning and operation. Usually mobile phone operators collect data for billing purposes, but we can use this type of data as a proxy to characterize the movement of vehicles, the movement of passengers, and also people in general. The biggest advantage of this mobile phone data set is we have, for example, active cell phone cards per 100 inhabitants globally. 96% of the population have access to mobile phone data sets. So what that means is we can actually trace the trajectory of roughly 96% of the population mobile phone holders in most part of the the world. So we have different type of data set associated to the cellular network. These data sets can be generated event-based. The data can be triggered by events when we make phone calls, when we receive phone calls, or when we send short message, or when we use internet. The other type of data is network generated. Telecom companies periodically detect their mobile phone devices to facilitate the mobile phone operation. If you can see on the right-hand side, I put a schematic for a cellular network. So most of the cell sectors are joined and made a location area. So when people are making a phone call and crossing the boundary of this cell sector, we can generate, for example, a handover information. Whenever people are using mobile phone and driving, we can trace their trajectory, and that kind of data can be used for our transportation planning and operation purposes. So one of the most commonly used data from the telecom companies are call detail record data. This data is usually collected by mobile phone providers for billing purposes. So whenever we make calls, the telecom companies have our location that is aggregated within the base station or within the cell tower area, or either with the cell sector or with the cell tower. We have also timestamp associated to our call, a location, the call duration, and so on. So using, for example, this kind of information, we can sense the trajectory of 50% of the population or 25% of the population, depending on my mobile phone penetration in each parts of the world. So here I put this small table to show advantage and disadvantage of survey-based data and the mobile phone data. For example, traditionally we use surveys to gather information about trips, the mobility behavior of people and vehicle. Traditional data or survey data provides detailed information. However, we have to invest a lot of money to gather that kind of information. And also that kind of information will be only captured for a short period of time. We don't have this kind of data frequently. Usually planners conduct surveys every 10 years or 5 years period from a small portion of the population. On the other hand, mobile phone data, we can collect data with a fine time resolution from a large portion of the population. Of course, mobile phone data has its own disadvantage. Travel demand modeling. I will discuss some of the most important techniques that has been implemented on research topics that used mobile phone data for transportation planning and operation, especially for passenger travel demand modeling. So one of the first steps when we use this mobile phone data is to detect whether a person is stationary or whether a person is moving or passing by a location. So in the literature, we usually call these terms detection of stay, detection of passing by areas, and so on. So the general idea is we have a raw trajectory data, mobile phone data. So we are using this data to infer people's mobility. The mobility, in a sense, we wanted to know the origin of the trip, the intermediate stop, as well as the destination of the trips. So we use a lot of researchers developed a set of algorithms to come up with these origin, intermediate stops, and destination locations. They use different type of thresholds to assume a person is stationary, person is moving, and also person arrived at this destination. This is an example that was done in the Senegal in Dakar. So we zoomed in the Dakar area, but we received a countrywide mobile phone data set from Senegal, and we were able to characterize this stay and pass by location for this country. The other important information we have to extract from mobile phone data set is the home, work, and other locations. So usually in transportation travel demand modeling, we estimate the commuting trips. In order to infer commuting trips, we have to identify the home and work location of people. So mobile phone data set has been very successful in terms of inferring the home and work location of most mobile phone users. Some of the techniques that has been implemented to infer the home and work location of mobile phone users include, for example, based on the frequency of mobile phone use during at night, during weekdays, and during the daytime on the weekend, people were able to infer the home location of mobile phone users. On the other hand, the work location of users can be inferred based on the number of times people use their mobile phone during working hours, and all the other locations were referred as others. So using this trip origin and destination, as well as home and work locations, we were able to identify three purposes. For example, home-based work trips, home-based other trips, non-home-based other trips. We were also able to extract trips to identify morning peak period trips, midday trips, and also afternoon peak period trips. And we feed this kind of information to develop a travel demand model for different cities and countries. This is an example of commuting trips by using that techniques I just discussed in the previous slides. We were able to infer the commuting trips for the whole country in Senegal. Recently, we extended our research to calculate the temporary and permanent migration flows using mobile phone data. We got a mobile phone data from a telecom company in Portugal, and we were able to infer the temporary migration and permanent migration associated to mobile phone users. We had a 14 months data in order to come up with this analysis. So using the change in the home location, we call that temporary migration. But if people within the 14 months, if people change their home location permanently, we call that a permanent migration. This was part of a master's thesis of one of my students, who was co-supervised by Dr. Sandhi from Chiang Mai University in Thailand. And this study is published in IEEE Access. So if the participants are interested, they can get that information. They can read this paper from those publications. Of course, there are some open challenges of studies that use mobile phone data for transportation planning and operation. One of the main challenges are limitations of mobile phone data in spatial and temporal accuracy. So the location information associated to this mobile phone data is given in a cell sector. So sometimes we only know the person who is receiving or calling, making a communication. We know within 100 or 200 meters radius. We don't know the exact location of the person. There are also some people, they are not frequent user of mobile phone data. So sometimes it's not possible to get enough data to make different type of analysis. The other challenge or limitation of this mobile phone data is lack of comparative data sets for validation. We can infer origin destination trips or different type of models, but there is a huge lack of secondary data to validate our results. The other problem is dealing with privacy issue. Most telecom companies, they don't want to share this kind of information because they don't want their clients, the location, the home and work location of their clients to be disclosed because due to this kind of research. Another limitation is we cannot access real-time data from these telecom companies. We usually work based on historical data sets. So before I move to the next topic, I would like to open the floor for some questions. So I'm happy to receive a couple of questions from the participants. Are there any questions so far?
Sir, as of now, we have not received any questions.
All right, so I will also pause for another question and answer sessions. So participant can also ask if they have any question by the end of the session, the presentation. So I will move to the next topic. So the next topic is freight track travel demand modeling using GPS data. So the previous section was using mobile phone data for travel demand modeling, passenger travel demand modeling. We also use this freight and commercial vehicle movement is also a data hungry field. We don't have data to properly model freight and commercial vehicle movements. So in recent times, we receive a lot of data, the likes of GPS data, to actually build travel demand models for freight, commercial vehicles, especially trucks. So I will discuss some of the research we did in my research group, and some of these research are published, so participants can further read about our research from these papers listed in the slide. So as you know, goods movement is an essential sector of the economy in most countries. And in order to support goods movement or freight movement, we build a lot of infrastructure. For example, we build rail, air, and pipelines, especially to distribute goods and different freight types to the destination. Trucks play an important role, and the focus of this study is modeling truck movement using GPS data. So compared to passenger transportation, larger trucks can have more impacts on our traffic. They can introduce a lot of congestion and also emit greenhouse gases and also damage the road. One of the main challenges to mitigate this type of impact is lack of adequate data on truck movement that provide information on the origin and destination of trucks, intermediate stops, or truck travel times, or commodity type, and so on. Traditionally, we collect this kind of information by conducting travel surveys, but travel surveys are usually expensive, and most of the tracking industries are willing to share their information because of this, the competitive nature of the freight industry or the logistic industry. In recent times, we were able to get an emerging alternative to traditional survey data that is passively collected GPS data. So the general goal of this study was to characterize the movement of truck movement using GPS data with these three specific study objectives. The first objective is to develop a set of algorithms to convert raw GPS trajectory data into track stops and track trips. The second objective is to analyze track travel patterns over time. So one of the advantage of having access to big data is we can study the patterns of movements over the period of 1 year. For example, in our case, we had access to GPS data from the track movements for 1 year, so we were able to analyze whether there is a change in the travel patterns of tracks over the period of 1 year. The third objective was to develop a trip distribution model based on the trips extracted from track GPS data for our travel demand models for commercial vehicle movement. So this is the methodology overview. Well, the methodology has 6 components. The first component of our methodology is data preparation. So we received raw data. So we did some data manipulation, including data cleaning in order to accurately, in order to clean the data so that it will be used for modeling and other analysis of our study. The second one is track stop detection, developing track stop detection algorithms. Then we also develop a set of algorithms to classify track stops into primary and secondary stops. Then we were able to generate track OD flows for different time periods. In our case, for 5 time periods of the day. That is based on the provincial travel demand model. Then using this track origin destination flow data, we were able to do trend analysis and develop destination choice models for 5 time of the day, time slots of the day. So to conduct this research, this particular research, we had a GPS trajectory data from 2 sources. From A3, we had a 4 months GPS data, and from SHOW tracking, we have a 12 months GPS trajectory data. In total, we were able to gather around 250 million GPS trajectories or GPS records. In addition to this GPS record data, we were able to obtain business establishment data for different type of businesses in Canada and the province of Alberta. We also had access to the provincial model, the Alberta Spatial and Economic Travel demand model outputs for the 2006, the base year. We obtained travel time and travel distance matrices data. We also have output from the trip generation model data. We use this different data sets to do our analysis. This is an example of a road track GPS trajectory data. As you can see, we have a 1-day data from October 4th. We plotted the GPS trajectory data on the province of Alberta in the middle, and on top of 2 major regions in Alberta, Edmonton and Calgary. Then the second model is a track stop detection model. So we developed a set of algorithms to convert raw GPS data into track stops. So what we did was we sort the GPS data for each track ID into a time series in order of date and time of GPS records. Then we were able to calculate the travel time, the travel distance, and travel speed between successive GPS records or GPS pings. And we use different type of criteria to determine a sort of event for each GPS records. Those events are related to whether the track is accelerating or decelerating, whether the track is stationary, whether the track is moving, and so on. Then we were able to identify the stop location for each tracks in our data sets. Then we plotted the detected track stops on top of the raw GPS data. And the have the raw GPS data on Calgary region. On figure B, we plotted the detected track stops on top of the raw data, and figure C shows the city of Calgary. Within the Calgary region, we plotted the detected stops on the city of Calgary. So for those of you who knows the Calgary, if you know the geography, these areas, the majority of the stops, the track stops are detected in the industrial region of the city, although we have track stops all over the city, but 50%, more than 50% of the track stops are detected in the industrial region or industrial zones of the city. So once we detected the track stops, we still don't know whether the stops are associated to goods movement. For example, whether the stops are related to loading and unloading. Some of the track stops might be also secondary stops, for example, drivers taking a rest or fueling their trucks and so on. So the second, after detecting the track stops, we developed another method to identify primary and secondary stops. So primary stops are areas where the truck stops to load and unload goods, and all the other stops, we categorize them as secondary stops. So we applied the concept of entropy. So the basic idea behind this concept of entropy is we clustered the stops associated to each business establishment. Then we try to see whether there is a heterogeneous carrier ID or a homogeneous carrier ID. So if there are diverse carrier IDs within that group of track stops, we say that might be associated to secondary stops. For example, trucks that are being operated by different carriers might access rest location. So we might have a carrier ID associated to different companies. So those areas might be related to secondary stops. But if it is a depot area, a loading and unloading area, most of the track stops might have the same carrier ID. So a homogeneous ID would be associated to primary stops. So in order to cluster the stops, we explored the use of clustering algorithm. In our case, we explored DB-scan and the K-means clustering algorithms to cluster the stops. After clustering the stops, we applied the entropy index. We calculated the entropy. So if there is more heterogeneity in terms of the carrier ID, we assign that stop secondary stop. If there is a homogeneous carrier ID within that cluster, we call that area track associated to primary stops. Then compared to the K-means clustering algorithm, the DB-scan algorithm provided a better result in terms of identifying track stops associated to each establishment or business establishment areas. So we calculated for each clusters the entropy index, and we randomly selected 150 clusters for validation. And in fact, we saw most of the primary stops have lower entropy index as expected. That means within each in the cluster or locations, we see a more homogeneous carrier ID. And the secondary stops have higher entropy index, showing in fact in those locations there are more than one carrier ID observed. So primarily those areas might be secondary stops. So once we classified the track stops into primary and secondary, we were able to construct our origin destination or trips information by connecting successive primary stops we were able to generate track origin destination flows. So this is an example of a track origin destination flow based on a week-long GPS trajectory data. On March 7, 2016, we plotted this information in the middle in the province of Alberta, and also in two major regions, Edmonton and Calgary. So after identifying these origin destination flows, the next in our methodology, the next topic is to do a trend analysis. So we have access to trajectory data for the period of 1 year. So one of the advantage of this type of data sets is we can use it to understand the characteristics of track movements across each day or each months of the year and so on. So our first analysis, trend analysis, was based on a correlation analysis. So we constructed track origin destination flow for 60 periods. So for each month, we were able to aggregate the track origin destination flow for 5 different periods, for morning periods, midday periods, afternoon, evening, and night periods. So for each month, we have origin destination matrices for 5 periods. Then for 12 months, we have a total of 60 origin destination matrices. So 60 for weekday and 60 for weekend days. Using these 60 origin destination flows for weekday and weekend, we were able to calculate the cross correlation values and self correlation values. So when we say cross correlation values, we measure the linear correlation between each origin destination flow from each time slot against the remaining 59 origin destination flows. In terms of self correlation, we compared the correlation between an odimetrics from AM period across all the morning origin destination flow matrices across 12 months. So in terms of self correlation values, we compared origin destination flows in the same time period across different months of the year, cross correlation, OD comparison across different time period and different months of the year. So one major takeaway from this analysis is we noticed there are more track OD flow variation over a typical day than within the same time period in different days. This is true for both weekdays and weekends. The second trend analysis is the previous one was done to compare origin destination flows. The second trend analysis was done to compare the trip generation and attraction roles of each traffic analysis zone. So in order to do that, we use an entropy measure again, and we calculated this entropy measure for each traffic analysis zone, and we compare this entropy measure across 12 months, and we try to see if there is a change in the trip generation roles of each traffic analysis zone within the province of Alberta. So to do this analysis, we segmented the province into 8 economic regions. So we have, for example, number 1, Wood Buffalo regions. We have 6 Calgary and 4 Edmonton. 6 and 4, Edmonton and Calgary, are 2 of the major regions in the province of Alberta. We use a total of 918 traffic analysis zone or study regions out of 3,271 traffic analysis zones. So this 918 traffic analysis zone actually accommodate more than 90% of the track movements in the region. All the other regions, they have a very low density of track movements, or most of them don't have any track movements from our sample. And the other reason we included this 918 traffic analysis zone is all these 918 traffic analysis zones or study regions have track trips for successive 12 months, then we will be able to do trend analysis. Then we constructed this track mobility transition graph to see whether there is a changes in the pattern of the trip generation roles of each traffic analysis zone across different months of the year. So the first column, you see we have the 8 economic regions. As you can see in this map, in this slide, I showed you 8 of the economic regions. Those are represented in the first column, and the second column is represents the traffic analysis zone, represented by the share of the trip generation role of each traffic analysis zone. Then we calculated the entropy value for each month. Then we plotted that entropy value across the months. Then we have, for example, for each traffic analysis zone, we have 12 entropy values. Then for that will be 918 times 12. Then we cluster those entropy values. We use a k-means clustering algorithm to cluster those values, and we see whether each entropy values fall into the same cluster across different months of the year. So as you can see, the dark red shows traffic analysis zone mobility pattern doesn't change throughout the year. It is a high entropy, but most of the high density regions, they have different type of destinations, a diverse destination, but the heterogeneity remain the same across the months of the year. The low density regions, they don't have a lot of tracking activities in terms of generating a lot of track. Then the last and the final analysis is development of a track trip distribution model. So for those of you from transportation engineering, you might be more, you might understand this better. So trip distribution is an important component of the travel demand models. So this is the second stage of the travel demand model for track travel demand or commercial vehicle travel demand modeling. So we use a destination choice model. This study attempts to develop a destination choice model for distributing track trips in the province of Alberta. So the main goal of this analysis is to explore the possibility of origin destination flows extracted from track trajectory data to develop track trip distribution model with a discrete choice model structure, such as multinomial logit structure. So the choices are among these 3,271 traffic analysis zone. So when we develop our destination choice model, the alternatives are, we have around 3,271 alternatives. We also use the observed trips from the track GPS trajectory data. We use around 52,000, more than 52,000 observed trips to build our model. This is the model structure for multinomial logit model structure. So the probability of trip going from the probability of a tracker taking a trip from origin I to J will be dependent on the utility associated to destination J and all the other destinations. So this is the utility function we built. And also once we have this aggregate utility, we can use the trip generation data from the travel demand model, from the asset model, and we can distribute that using this calculated probability. So we build the utility function using different type of variables. The first variable is impedance variable, that is travel time between origin zone to destination zone. We also use a size variable. So the size variable describes the tracking opportunity at the destination. So this size variable is represented by trip destination ends as estimated by the trip generation model of the asset model. The asset model is the travel demand model for the province, for Alberta. We also major city, and other city to other city. These dummy variables are included to measure the strengths of tracking interaction between major and minor cities. Then we estimated destination choice model for 5 different periods of the day for the whole province. For the AM period, the midday period, the afternoon peak period, evening and night period. We estimated 5 different models. As you can see, all of the models have a reasonably high rho squared value that shows the model fits the data very well. And also most of the impedance variable and the size variables are statistically significant with 95% confidence interval. For example, the size variable is trackers would choose a destination that has high tracking activities. And also the impedance variable in all the models is negative. That shows trackers would prefer to go to a destination that is closer compared to a very far destinations. For model performance evaluation, we were able to compare the trip length frequency distribution against the estimated and the observed trip lengths that is measured in terms of travel time. For all our models, we saw the model properly replicate the observed travel distances. This is for AM model. This is the midday and PM model, evening and night model. So the contribution of this study is we were able to use the GPS trajectory data as well as model outputs from the traditional, provincial travel demand model. We were able to combine these in order to enrich the set of variables that are available for modeling track movements. We also develop a set of algorithms to identify components of tracking, including track stops, track stop types, track trips, and other tracking activities. We were also able to develop 2 metrics to study province-wide track travel patterns over the period of 1 year, which is used to determine whether there are changes in track travel patterns. And finally, we were able to use trips generated from track trajectory data to develop a destination choice model to distribute tracks in the province of Alberta. There are some future directions to improve this study. One of the future research direction is to explore model stratification by vehicle type and by trip purposes, and of course to do more model calibration and validation. So before I move to the next topic, I will again pause. I would like to pause for question and answer. If anybody has any question, you are welcome.
Let me ask the participants. Participants, any question? Okay, I guess. Please take this opportunity and take maximum benefit. So if you have any question, you can ask. Don't hesitate.
Yeah, so I will continue my presentation. If anybody has
one question is there, sir. Like a developing country like India, how we get this freight vehicle movement data from GPS.
Okay, maybe let me see. Okay, the question is, how can we have access to this type of GPS data sets, right?
Correct.
Yeah, so for our study, for example, for this particular study, we get the data from the Alberta Transportation. Alberta Transportation is a transportation agency that develops model for the whole province. We get the shout tracking data from Alberta Transportation, but the other 4 months data, we actually bought it from A3. A3 is American Transportation Research Institute. That might be, I think, a little bit expensive. For example, we spent for 4 months data, we spent 10,000 Canadian dollars to buy the data. Yeah.
One more question is regarding sustainable development globally to meet in COP26. What are the initiatives in the future in the transportation department?
Sorry, can you repeat the question?
Regarding sustainable development globally to meet COP26. What are the initiatives in the future in the transportation department? I guess not relevant to the theme, but in general, they want to know.
Yeah, so I think the question is related to how to address, maybe basically I mentioned at some point, GHG emission, greenhouse gas emission associated to track movements. For example, in Canada, of all the sectors, the transportation sectors is one of the major pollutants in terms of greenhouse gas emission. And there are different type of strategies, mitigation strategies that are being implemented by the country. And also there are so many research to support this kind of research. For example, there are some activities in terms of vehicle technology, for example, using electric vehicle, type of efficient fuel technologies. In terms of, for example, freight movement, commercial vehicle movement. In Alberta, for example, there is a huge research in terms of changing the fuel economy from diesel and fossil fuel into hydrogen fuel cell technology, hydrogen fuel cell economy, such that we can cut down emission and greenhouse gas emission to have a more sustainable transportation system in terms of the freight industry.
Okay. Again, that data related question is that how, for a developing country like India, do we have any other method or other source? Because we have only data of origin and destination from various transportation companies.
For example, my first research topic, for example, in terms of using mobile phone data to develop travel demand models, actually, those type of analysis are more relevant for developing country. The likes of India, for example, the telecom companies are more advanced. The country might be developing, but the telecom industries are very strong. The transportation agencies can communicate with the telecom companies to access mobile phone data to do these travel demand models, because conducting travel surveys for each region might be very expensive. And usually these travel surveys, they can only be done once in every 5 years or once in every 10 years. So we can use the type of mobile phone data set or other opportunistic data set as a proxy to understand the movement of people and develop our travel demand models or update our travel demand models. So developing countries than developed nations. So most developed nations, they actually can do these travel surveys. Their economy support those kind of analysis. But developing countries could take advantage of these emerging technologies and opportunistic data sets to support their transportation planning and operation. Are there any other questions?
Yeah, one more. Looking towards the income and literacy rate, our truck operators might only get mobile data, though call data, as they might not use internet more in this case. Is this data relevant? Because
Okay. As I mentioned, from the telecom companies, from mobile phone companies, we can have different type of data sets. One of the most commonly used data sets for transportation planning and operation is call detail records data. So that call detail records data is associated to call and SMS, not internet data usage related data. So as long as we have call communication, voice call, and SMS, short message service, those data can generate a huge data that can sense the movement of the large portion of the population. So we don't have to use internet usage data to do this travel demand, to estimate these travel demand models.
okay, I hope participants are satisfied. Because in a developing country like India, this data, they are very reserved from the privacy point of view, and only police authorities are given this data. So till date, we have not approached to any mobile company, or we don't have systematic transporting agency, central agency or state level agency who can approach the telecom companies and ask this data, right? So that is the
Yeah.
problem, right?
I think, yeah,
Yeah.
it makes sense. So I think I see one more question on the chat window. Does rate of voice call and SMS affect data collection? So the mobile phone, the telecom companies, they will always collect this information for billing purposes. Whether a person used the mobile phone once in a month or 100 times per day, they will still save this data. Of course, the more interaction we have for the sake of transportation modeling, the data will be more useful. That means we have more information about the trajectory of the person or the trajectory of the vehicle. So if we have more, if the rate of voice call and SMS increases, the information will be more valuable. But if we have only limited number of calls or SMS, we have limited number of information about the movement of the vehicle or the passenger or the person. So it will not affect the data collection process because we are accessing historical data that was collected by the telecom companies, but the rate of voice call and SMS information, SMS short message services will affect the quality of the data for transportation planning.
Okay. Any other questions? Okay. Thank you, Merkebe. You can continue with your next session, sir.
All right. So thank you very much. So I will move to the next topic. So the next topic is estimating potential demand for dockless scooter sharing service. So as most of you might know, in recent times, especially in the last couple of years, since 2018-19, these shared electric scooter and electric bike services are becoming very popular in most parts of the city, especially in the North America. In Calgary, scooter has been very popular and many people have been using it, especially just before the pandemic, the COVID pandemic. And the transportation planners, the city officials were very surprised. It was so unexpected because we don't have, for example, existing models that could address the impact of this emerging transportation technology on our transportation system. So we were intrigued and we were motivated to do some sort of research with the following two objectives. The first objective was, where are the potential scooter sharing service users in Calgary, in the city of Calgary? And also we wanted to know what is the current coverage of supporting scooter service infrastructure in this area. So one of the reasons we have this objective was we noticed the majority of the scooter services are concentrated in the downtown area. And we wondered, why aren't people living in the other quadrants of the city were using scooters like the people who are actually using them in the downtown area? So we had access to the shared electric scooter data from the city of Calgary. There was 2 electric scooter providers in Calgary, Lime and Bird. They were operating in 2009 around 1,500 scooter devices. We had access to a 3 months data from their operation. We did some kind of data cleaning activities. We removed data. We removed those trips that are less than that lasts fewer than 30 seconds or 100 meters. We also removed those trips that are more than 2 hours, that took more than 2 hours or 40 kilometers. So due to these data cleaning activities, we removed around 0.15% of the data. Then we did some sort of exploratory data analysis. We tried to analyze the citywide average hourly number of electric scooter trips. As you can see, the patterns of the weekday trips are a little bit different than the patterns of the weekend trips. The weekday trips, we have morning peak, and the rest of the day we have still a lot of scooter usage. The weekend pattern, we have most of the scooter related trips that happens afternoon up to midnight actually. So the scooter trips are a little bit different. The characteristics of scooter trips are a little bit different compared to other traditional transportation modes. For example, transit or personal vehicle use. Usually from traditional transportation modes, we have morning and afternoon peak and some traffic in the midday. But in terms of scooters, we have large number of trips that are happening, for example, around 9 p.m., which is not usual. So we wanted to study more about the behavior of these trips. We also try to see the trip lengths associated to these scooter trips. Most of the average trip lengths of shared electric scooter service is 1.85 kilometers, which is very short. So this might be due to many people using scooters to move around the downtown area, or they are using them as a last and first mile to connect with Calgary. As you can see, the trips are the same across the days of the week, and the majority of the trips are concentrated at the downtown area. In fact, more than 90% of the trips are concentrated in the central part of the city, and the other quadrant of the city, they don't see a lot of scooter trips. Then we wanted to measure the potential demand for scooter sharing service. As you can see, most of the trips are concentrated in the downtown area. Then we wondered maybe this happened because the other quadrant of the city, people are not using scooters on those parts of the city because there is no supportive scooter infrastructures. For example, bike lanes or different type of pathways and walkways. Then in order to do that, we wanted to develop a potential demand index for each parts of the city. To develop this potential demand index, we follow these two steps. The first step is analysis of factors that influence the shared electric scooter usage. We use regression model to understand the influencing factors of scooter usage. And the second one is using that information, we examine the magnitude and distribution, spatial distribution of potential demand. So as you can see in equation 1, we use a regression model. Y represents the number of hourly electric scooter trips in the morning or afternoon peak period. Then we divided the regression model into two. So the first part, that is X, represents, V represents the second part, for example, influencing factor related to scooter or cycling infrastructure. So the explanatory variables are associated to infrastructure, bike lane, cycling track, pathways, and so on. The first components are all the other variables related to land use type, land use mix, population, and employment densities. So what we wanted to do is we wanted to see different parts of the city that has a similar land use mix, land use type, population, and employment density characteristics, characteristics that is similar to the downtown area. But if they have those kind of characteristics but lack supportive scooter infrastructure, maybe that is the main reason why people are not using this kind of modes in that part of the city. So this potential demand index is represented by this component, and it measures potential demand for shared electric scooter service in each community district. So people wanted to drive, use scooters, but since they don't have proper infrastructure, they are not using it in those areas. There is demand, potentially there are some people, they may be using scooters in those areas, but they are not using it right now because of lack of infrastructure. Then we use we explore different type of explanatory variables to estimate our regression model. The first group of explanatory variables are demographic and socioeconomic variables. So we explored population density, employment density, and also some of the scooter users are tourists. They are not residents of Calgary or people who work in Calgary. So in order to capture activities associated to tourists, we use a Foursquare check-in count data. We thought maybe tourists use different type of social media, and we might be able to capture that kind of information if we incorporate this kind of variable. The second group of variable we use is transportation infrastructure variable. So we use different variant of lengths of cycling track, bike lanes, and so on, different type of infrastructure related variables. The third group of variables are the built environment. So the built environments are related to point of interests. We measured the number of point of interests around different transit stops. why we did, the reason we did this type of, we created this type of explanatory variable is we thought most of the people might be using scooter to access as a first and last mile. So we have to understand how many point of interests are available around each transit stop. Maybe that would influence the use of scooter usage in the vicinity of transit stops. We also incorporated floor area ratio of different type of land areas to measure the influence of these factors on shared electric scooter usage. Then we estimated the regression model. We were able to identify some explanatory variable that influences scooter usage. Using this information, we were able to develop the potential demand index. So the potential demand index is supposed to measure, there are in fact demand in those community districts. I call these community districts parts of different parts of the city of Calgary region. So the potential demand index shows if there are high potential demand in that area, that means that area actually has the characteristics that invites scooter usage. But if it has no demand currently, that means these areas require in the future requires attention, and planners should prioritize their projects to build scooter or bike supporting infrastructure in those areas. And we thought this kind of information would help city authorities and transportation planners. It will be one of the indicators to prioritize projects in the future if the city plan to build those kind of infrastructure. So the contribution of these studies, we bring together multi-source data, including electric scooter GPS data, open and crowdsourced geospatial data, for example, Foursquare checking count data, point of interests, land cover, general transit feed specification data, cycling infrastructure, to enrich a set of variables that are available to develop a scooter travel demand modeling. This study also shows how to develop a potential demand index measure that might be helpful for city officials and planners in the future. So I concluded so some of the long-term vision of my research group in the University of Calgary is to advance our ability to model emerging mobility services and analyze the impact of these emerging mobility services and technologies to proactively plan their introduction, management and operation, and meet the transportation sustainability goals. So there are different type of short and long-term objectives for my research program. So some of the research questions I would like to answer in the future are related to demand, short-term demand prediction for emerging mobility services, and also to develop a unified framework to assess the equity performance of these emerging mobility services and technologies. So if some of the students from your university would like to apply to work with me as a master's student or PhD student, this would be the type of research I would like to work in the future. That's why I put these slides to communicate with the research community or the participant in this workshop. So that concludes my talk for today. If you have any questions, you are welcome. And I would like to answer or discuss your questions.
Okay. So participants, any questions related to entire topic, or if you have doubts regarding this, you can discuss. You can take this opportunity as a golden opportunity because we are talking with international speakers. So please use this opportunity to solve your doubts. Any of the participants, if they have any question, they can ask. Okay. So we are not getting, I think, one chat. No. That is the feedback form. Okay, one question is there. Any IoT technique used in transport sector in future?
So in my research group, we don't have that, but so IoT, I see it like making our transportation system to see, to hear, to communicate with other facilities. So in terms of, for example, public transit, we are equipping our transit vehicles with different type of technologies so that they can communicate in terms of passenger counting system and also automatic vehicle location system. So we have those kind of huge, the transit sector especially is one of the agencies that generates those kind of information, and it can communicate with a central system and there is a real-time information. So somehow that is related to that IoT infrastructure.
Okay. Any other question? Can we use radio frequency identity for travel data?
Yes, and so for travel demand modeling, we can use any type of information as a proxy, as long as that information can tell us the origin of the trip, the destination of the trip, or a frequently visited locations. So all the information these days can be used as a proxy to detect movement or activity locations. Of course, we can use it for as a travel data.
Okay. Any other question you can please write down, or you can unmute and ask question directly. No more questions? Okay, I guess there are no more questions. So, Dr. Merkebe, thank you once again. You nicely presented your lecture in 3 segments. In first part, you discussed how mobile data can be used to predict the origin, destination, and other surveys, and to predict the transport behavior. In the next session, you use GPS data for trucks trips, and you analyze that. And in the last one, you analyze the electric scooters analysis. So thank you very much. And I think we have one more question. What should be the minimum sample size for travel data?
I think it depends on, for example, for provincial travel demand model or for regional travel demand models, usually we survey more than 5% of the population to understand the travel behavior of the city residents. So usually we have more than 5% of the general population. But it depends on study to study. For example, if you are using some machine learning algorithms to predict demand, to predict traffic, we might need a lot of data, input data to train our machine, to train our model. So the more the data, the more the machines learn and the more the prediction accuracy. Well, in fact, we have to be careful about overfitting our model. But for traditional travel demand models, when we carry out travel surveys, we usually target 5% of the population, to survey 5% of the population.
So I hope you got the answer, Ravindra, sir. Okay. And thank you once again, Dr. Merkebe, for saying that you are ready to guide a few of our MTech and PhD candidates in your domain area. So thank you for giving that opportunity also to our participants. And one more question came. How can we decide the freight movement of a city? On which parameter it is depending specifically?
Yeah, I think this question is more generic. So the freight movement in a city, we have different type of freight movement. For example, in our provincial travel demand model, we group, for example, long and short distance travel models. That is the first category. We develop model for short trips and long trips. Then we develop model for different vehicle types, medium, long, heavy duty vehicle, medium duty vehicle, and small trucks. We also develop different type of models for those kind of service or freight or other type of, for example, other type of activities. And we also develop model, we can stratify it for those traffic that are concentrated in the city area, and also for long ranging trips. And also some of the freight trips are related to, for example, postal delivery. So we have not one trip, we have multiple trips. So we have to stratify our model and customize for each type of vehicle and for each trip purposes.
Okay. Any more question, Ravindra sir? Then type quickly. Okay, he is satisfied. Any other participants before we conclude? You all are free to ask questions. Please take this opportunity. Okay, so finally we come to an end of this session. So again, thank you for all. Thank you for sparing your time, your energy, and your expertise. Thank you very much, Dr. Merkebe. And hope for this cooperation will survive in future also, right? And we will have many more interactions.
Yeah, thank you for the invitation. So I hope to collaborate and also make presentation in the future and continue collaborating with your department and university.
Yeah. Sure.
All right. Thank you everyone for attending the session.
Yeah. Thank you, sir. Bye.
Okay, bye.
And for participants, we will meet for the next presentation sharp at 11:30 a.m. Right? So till then, you can have a tea break, small, and we will meet at 11:30 sharp. Thank you.